Good day everyone. Today I will be presenting the biomedical signal processing circuit and explaining how each stage processes the input signal. Throughout this presentation, I will explain the function of each circuit stage, calculate the voltage gain of the operational amplifiers using the gain equations, and compare the calculations with the oscilloscope measurements obtained during the experiment. The experiment was first carried out using a function generator set to 200 millivolts peak to peak at 1 kHz. Measurements were taken at different test points throughout the circuit using an oscilloscope to observe how the signal changes after each stage. After completing the first experiment, the same procedure was repeated using an input of 200 millivolts peak to peak at 200 Hz. The results from both experiments will then be compared to observe how the change in frequency affects the circuit. Before discussing the measurements, here's a brief overview of the circuit. The signal first passes through a non-inverting preamplifier, followed by an inverting amplifier that provides additional adjustable gain. The signal is then sent through a second-order Sallen-Key low-pass filter to reduce unwanted high-frequency components before entering the audio amplifier, which provides the final amplification at the output. I will now be testing 200 MV at 1 kHz. At testing points 1 and 2, the first stage of the circuit is a non-inverting amplifier using an operational amplifier. Its purpose is to increase the signal amplitude while keeping the output in phase with the input. The voltage gain of a non-inverting amplifier is calculated using the equation AV equals to 1 plus RF over Rin. Using the resistor values in the circuit, where R2 is 220 kilo ohms and R3 is 10 kilo ohms, the voltage gain should be 1 plus 220K divided by 10K, which is 23. This means the amplifier should increase the input voltage by approximately 23 times. Therefore, a 200 millivolt input is supposed to produce an output of approximately 4.6 volts. During the measurements between test points 1 and test points 2, channel 1 measured 200 millivolts, while channel 2 measured approximately 3.6 volts. Both waveforms remain sinusoidal and in phase, confirming that the preamplifier successfully amplified the signal without introducing any phase shift. Although the measured voltage is slightly lower than the value expected, this is because of practical component tolerances, capacitor loading effects, and the non-ideal characteristics of the operational amplifier. Capacitor C2 is connected across the feedback resistor. As the frequency increases, its impedance decreases slightly, helping reduce high frequency gain, improve circuit stability, and suppress unwanted noises. Now I will be testing TP2 and TP3. The signal enters the second stage, which is an inverting amplifier, using another operational amplifier. The voltage gain of an inverting amplifier is calculated using the equation AV equals to minus RF over Rin. The negative sign indicates that the output waveform is shifted by 180 degrees. This stage also includes the potentiometer P1, which forms part of the feedback network. Adjusting P1 changes the feedback resistance, which changes the voltage gain. Increasing the feedback resistance increases the gain, while decreasing it reduces the gain. Between test points 2 and 3, channel 1 measured 3.6 volts, while channel 2 measured 5.28 volts. The waveform at test point 3 remained sinusoidal, but was shifted by 180 degrees, confirming that the circuit is functioning as an inverting amplifier while providing additional amplification. Now we test TP3 to TP4. The signal passes through a second-order Sallen-Key active low-pass filter. Unlike the previous stages, this circuit is designed mainly for filtering rather than amplification. Its purpose is to remove unwanted high-frequency noise while allowing useful low-frequency signals to pass through. Using the resistor value of 22.6 kilo ohms and the capacitor value of 5 nanofarads, the cutoff frequency is 1.4 kHz. Between test points 3 and 4, the signal amplitude decreased from 4.96 volts to 4 volts, while both waveforms remain in phase. This slight attenuation is expected because the input frequency of 1 kHz is close to the filter's cutoff frequency. As a result, some attenuation occurs while the waveform remains clean and undistorted. Now we test TP4 and TP5, which is the final stage that uses an audio amplifier. Unlike the previous operational amplifiers, the audio amplifier provides both voltage gain and current gain, allowing it to produce a stronger output signal. Capacitor C13 connected between pins 1 and 8 increases the internal gain of the audio amplifier, while potentiometer P2 controls the signal level entering the amplifier. Between test points 4 and 5, the signal increases from 4 volts to 7.2 volts, confirming that the audio amplifier successfully amplified the signal. Finally, for TP1 to TP5, comparing the test points 1 with test point 5, which is test point 1 with originally 200 millivolts input signal, was amplified to approximately 7.2 volts. The output waveform was also inverted relative to the input because of the inverting amplifier. Initially, the output waveform was clipped because the amplifier gain was too high. When the amplifier attempts to produce an output voltage greater than its supply voltage, it enters saturation, causing the peaks of the sine wave to become flattened. By adjusting potentiometers P1 and P2 slowly and carefully, the gain was reduced until the amplifier returned to its linear operating region. This restored the clipped waveform into a complete and undistorted wave. Now we set the function gen to 200 MV at 200 Hz. From TP1 to TP2, the channel 1 remained at 200 millivolts, while channel 2 increased to about 4.64 volts. Both waveforms remained in phase, confirming that the preamplifier continued to operate correctly at the lower input frequency. From TP2 to TP3, the output measured about 5.28 volts and was once again shifted by 180 degrees. This confirms that the inverting amplifier continued to provide amplification and phase inversion, just as observed during the first experiment. From TP3 to TP4, the signal decreased slightly from approximately 5.28 volts to 4.8 volts. Compared with the 1 kHz measurement, the attenuation is smaller because 200 Hz is well below the filter's cutoff frequency of approximately 1.4 kHz. This allows the signal to pass through the filter with minimal attenuation while still remaining a clean sinusoidal wave. Between test points 4 and 5, the output initially measured approximately 7.92 volts, but the waveform became clipped because the amplifier gain was too high. After carefully adjusting potentiometers P1 and P2, the clipping disappeared and the waveform returned to a clean sine wave with a peak-to-peak voltage of 7.44 volts. Finally, we compare test points 1 and 5 and the signal was once again amplified significantly while maintaining its sine wave. The output remained inverted because of the inverting amplifier state. In conclusion, the biomedical signal processing circuit was a success. The first stage amplifies the input signal while maintaining its phase. The second stage provides additional adjustable gain and introduces a 180-degree phase shift. The third stage removes unwanted high frequency, components. And the final stage provides the final amplification required for the output. Overall, the circuit successfully amplified, filtered, and conditioned the input signal, demonstrating the fundamental principles of biomedical signal processing. Thank you.